So I would like to thank the organizer again and for the opportunity to present our work. So again, I'm excited to present our ongoing project, which is led by Professor Andrei Khrenikov, and mainly it is a relational theory, which shows surprising results and is consistent in describing classical and quantum phenomena. So our theory relies, basically, the most important principle is the Leibniz principle. We are using relational, and our perspective is relational and event interpretation of physical theories. And we also adhere to Bohr's viewpoint on outcomes of measurements. We use the ontic epistemic structuring of scientific theories, and we operate solely on p-adic field of number field. So our program is still being developed, and we get a lot of results, and but we already showed in a few papers interesting results, but because we have so many at least numerical results, and interesting numerical results, I will mainly present our fundamental concepts and not go deeply into the analysis, and our fundamental concepts I will present, and key result consequences. So actually we started, our starting point was the representation of data collected in medical studies by dendrograms with the aid of clustering algorithms, and we encoded the branches of trees by p-adic numbers, which are natural numbers with p-adic distance between them, and we constructed the Brownian potential on p-adics, and it was used for medical diagnosis of mental diseases. Actually, so instead of time series of real numbers, we represent experimental data by dendrograms, which are generated by hierarchic clustering algorithms. And we study hierarchic relations inside datasets and don't simply order with respect to position on the real line. The analysis led us to some theoretical and philosophical conclusion on foundation of classical and quantum physics and their interrelations, so the interrelation between quantum and classical physics. And we see that the degree of quantumness, which is checked by the aid of different tests like the Beilinson inequality, so these tests are very similar to ordinary tests of formalizing random sequences, especially a batch of statistical tests. So it's just a kind of a statistical test. What we very abstractly and heuristically do is we have some data, we have measurements or events, and we choose some pre-chosen, we choose some distance metric, we choose some clustering, algorithm, and we construct this structure, which we call dendrogram, which gives the relation between each event to any other event we observe. Each event is encoded with a string of 0 and 1s in the case of the two-adic field, and then we can encode it as a p-adic number. So according to Bohr, the outcomes of measurements are not the objective properties of the system, and they quantitatively represent the interrelation between the system and the observer. And we shall use the ontic epistemic structuring of scientific theories, where the ontic description is observer-independent description of reality, and the observer can construct its approximate epistemic representation of the ontic description by collecting more and more data. We extend the Copenhagen interpretation, so where the observer can have the free choice to perform or not to perform an observation, but he has in our theory also the free choice to decompose some of his collected data into blocks and to treat these blocks as a system, as systems. Our fundamental entities of the epistemic theory are events, not systems, and which is very close to the causal set theory, and events are hierarchically interrelated with the aid of clustering algorithms. Different algorithms can generate different relational structure, but our numerical simulations show that the properties of this epistemic universe generated by different clustering algorithms do not differ. So the standard periodic ultrametric where P is greater than 1 and is a natural number is introduced in the following way. X is a sequence of A's, Y is a sequence of B's, where AJ and BJ can have any natural number between 0 and P minus 1. And we have the distance between these two sequences as P in the power of minus K for K, where K is the component where the two sequences start to be different. So this is not only a metric, it's also ultrametric, and it satisfies a strong triangle inequality for any three XYZ sequences. This is the tree-like representation of our two-adic space, where it grows infinitely, branches infinitely. And in this strange geometrical field, there are some very nice properties. So all triangles are isoscales, and each point in a ball can be selected as its center. Geometrically, a ball is a patch of infinite branches having a finite common root branch. And such spaces are disordered, totally disconnected, and having zero topological dimension. So, although they are very strange spaces, they arise very naturally in regular data analysis from data series with application of clustering algorithms. Sequences are represented as numbers given by series with respect to powers of P's, and they converge in the periodic metric. The limit of the growing dendrogram is the ontic representation of the universe, and the finite dendrogram are epistemic representation of growing complexity. And the points of the periodic fields are elementary ontic events, where subsets of these points are ontic systems. Now, in the epistemic case, endpoints of branches of such dendrograms are epistemic elementary events, and the sets of these points are epistemic systems. So, an epistemic point event is actually a coarse grade representation of an infinite batch of ontic events. Actually, in the limit, an observer can construct the ontic description. The dendrogram-based epistemic theory leads to the periodic geometry of the ontic universe, and in the limit, the dendrogram of increasing size generates the infinite periodic tree endowed with a periodic ultrametric. So in our epistemic model, the sharp classical quantum separation disappears. The degree of classicality is based actually on the system's complexity, the size and the topological complexity of its dendrogram representation. So if we have an observer which decomposes its data into very small and simple blocks, and another observer who does the same, they have correlations between them, which we can test by the CHSH violation. And and if we make the blocks larger, then the CHSH violation will go to decrease. So the degree of classicality is based on the system complexity, the size and topological complexity of its dendrogram representation. Quantum systems are characterized by a low complexity of their dendrogram, and very simple hierarchical relational structure behave as quantum in some measurements, even if the system has classical origin. In our approach, even classical physical systems can exhibit quantum behavior within a hierarchical representation of experimental data. So DH theory provides the possibility of introducing hidden variables behind any experimental data. Actually, these hidden variables are the relations between the events. Straightforwardly, it seems that Bell-type inequalities cannot be violated under the assumption of locality. However, we showed that the violation of the CHSH inequality for special selection of settings can be achieved, and we showed that the reason for this is precisely the violation of ergodicity. So the measure theoretic and the frequency averages do not coincide. Basically, so our dendrogram approach to general relativity basically considers geodesics corresponding to some metric of general relativity and represent each of them by dendrogram, as on the side figure. So we have some coarse-grained events on spacetime, and we studied some features of dendrogram representation of geometry around the Schwarzschild black hole, and we found this, so the dendrogram branches can be interpreted as information streams and encoded events. Thus, DH theory is a kind of informational model of general relativity. We found a surprising informational interrelation between fundamental constants and their DH analogs. So within very nice precisions, and since the usual quantum mechanics can be imagined from DH theory, general relativity can be represented with quantum formalism as Brownian mechanics. So again, we use the dendrogramic analog of the action principle, which is suggested by Smolin in his causal set theory, and we showed that the periodic chronological path which describes geodesics is in fact maximal, and actually what it says that on the dendrogram chronologically we jump from one event to the most similar event available, and from the dendrogram we could construct a periodic coordinates via from this periodic analog of Smolin's action principle. These periodic coordinates show high correlation and fit with the real space-time coordinates. We have a newly released investigation which shows that analytically we generalized the quantum mechanical emergence scheme developed by Smolin, and in our scheme we quantized not events but the differences between them, and through analytical derivation we arrived to Brownian mechanics. Moreover, we studied the dynamics, so via numerical simulation, the dynamics of the event universe generated by the appearance of new events. So we have a dendrogram, and we have another event which creates a dendrogram with one more branch. Generally, each new event can generate a complete reconstruction of the whole dendrogramic universe. So, and the elementary events created up to the most, so the dynamics that are local in the physical space become non-local in the dendrogram space. So all events are permanently in dynamic motion on the dendrogram, and then events that happened a billion years ago is not frozen in the dendrogram space, and the contemporary events disturb it, and vice versa. The position of a newly generated event in the dendrogram space is determined by all previous events, and the appearance of a new event does not generate, but the appearance of a newly generated event does not generate a totally random distribution of events. So there is some probability, there is high probability not to redistribute all events. Okay.
Including questions.
Yeah, okay. So only very special dendrogramic configuration can be created with high probability. And so in the course of evolution, the dendrogram complexity increases and determines the error of time in the event universe. We use the complexity measure from particle shape dynamics, where DH theory and particle shape dynamics are both relational theories and relies on Mach principle and Leibniz relationalism. And by using the complexity measure on dendrograms and its periodic string representation, we demonstrated the emergence of time error from the periodic zero-dimensional field where space and time are absent. So I will just go through our main results and consequences. We identified the Bohemian explicate and implicate order very simply in connection with epistemic ontic description of the universe. Moreover, we showed each explicate level contains the information of lower explicate order and vice versa. We identified the periodic quantum potential as a structural property of the dendrogramic relational structure. We demonstrated that dendrogram representation of classical data violates CHSH inequality, and we showed that the hidden hierarchical relations are non-ergodic. We represented the general relativity dynamics along geodesics in relational periodic way, and the dynamics on dendrograms are emergent from just a simple action principle. And we showed that the emergence periodic coordinates from the action principle correspond well with the real space-time coordinates. We demonstrated the emergence of time error, and we generalized the quantum mechanical emergence stream developed by Smolin, and we derived Bohemian mechanics. So this is my final slide, and just to note that we made only the first steps in the development of this dendrogramic model, but our main tools were numerical simulation, but recently we started also analytical reasoning of this theory. We started starting with geodesics, of some general relativity metric, we constructed the corresponding dendrogramic representation, which can serve as a base of the general relativity quantization via the emergence of quantum mechanics from DH theory. Moreover, we modeled the relational recombination of dendrogramic universe generated by the appearance of new event, and although such event disturbs the past event tree, statistically recombination are not global, and we observe actually in the data some kind of relational smoothness in evolution of the universe. By introducing shape complexity for dendrograms, we are able to determine the error of time.
Thank you very much. Okay, well, we have time for one or two questions. Would you like to go ahead?
Thank you for the talk. I just had a quick question. I was trying to understand conceptually what's happening. So you propose an extension to the Copenhagen interpretation wherein the experimentalist can decompose the data into many, many blocks. So my first question is that the one who gets the data in a causal fashion, right? Like, so at time t, I get this much amount of data, and then in 10 more minutes, I get more data. And so I'm trying to understand in your analysis, do you take that into account to get the error of time, or?
Of course. So when we did the CHSH violation simulation, so when we did the CHSH violation simulation, we took the whole data. So each observer, we had 2 observers, Alice and Bob. They acquired classical data. Then we decomposed the data into very simple structures. So we had like a time series of very simple structures for Alice and Bob, and then we defined some observable on these simple structures, and we found that some of the features that these observable give us a violation, not all of them. And so some of the features, and if it is very simple, structures, we have a percentage of features which is large. And if it is very complex, then that violates the CHSH inequality. And if it's very complex, then we do not have. So there is some kind of a very, very nice transition between randomness to classical.
How do you get this data? I completely miss how you get your data.
I take any classical data. So I can take a random sequence of
if you want to test CHSH, it should be a data relevant for CHSH. You cannot look at I don't know, the broken radio.
we take each structure as each structure. We have the algorithm. It is very complex, this algorithm, but each structure actually gives us 1 or 0, like in the Bell experiment.
Sorry, completely miss it.
I think we have to ask for the controversies to be resolved privately and go to lunch now. Thank you for your talk.
Okay.